Yeah. There, for certain reasons, I don't want to talk about it now, but if you won't be able to sleep at night, stick around after class and we'll answer your questions. Were you back there all this time? Okay. Because I asked people to raise their hand. Yeah, I raised. You did. Okay, I did. I'm sorry. No problem. You're all done? Yeah. Okay. Okay, well, that answers my other question.
Whoa,
So, first order of business is, are there any questions about the homework?
Yeah, of course.
Okay, so if you want to tell me in particular?
Can you do question 2?
Okay.
And 38.
Okay, hold on, one at a time. So question 2 on 8.4, page 558. I have to tell you, I have to admit, I kind of wound myself up in, well, it wasn't this problem. It was another assignment. I wound myself up in stitches. Everybody's answer was different from mine, and I couldn't figure it out. And then finally I realized the problem said sine, and I had said cosine. So I'm subject to errors. Okay, so there we go. Okay. So problem 2 says f of theta equals cosine of 2 theta, where theta is in radians. And so there's some questions. What is the period, amplitude, the frequency, and the equation of the midline? Okay, let's take them one at a time. The period. So I think we talked about this. The period for sine and cosine, where this number is 1, is 2 pi, and when you have a number that's not 1 here, you divide by it. So the period will be pi. The amplitude, that's the number out front, which of course is just a 1. So the amplitude will be 1. The frequency, well, once you know the period, the frequency is easy. Frequency is just 1 over the period, so it's 1 over pi. And what is the equation of the midline? Well, there's no, remember the d value here? D is 0, so it's just going to be y equals d, or 0. Okay, what are the maximum and minimum values? Well, they're going to be the midline plus the amplitude and minus the amplitude. So the max is going to be 1, and the min will be minus 1. Graph the function without using a calculator. It's like count on your fingers while making a fist, right? Okay. So here's the xy axis, and I don't have to draw the midline because that's just the x-axis. The amplitude is plus or minus 1, so I'm going to draw in a little dotted line here so I know what I'm going between. I'm going to need some values on the x-axis. It's not necessary for this to be square. We're just trying to show what's going on. So you make this pi, 2 pi, pi over 2, so forth. So it being a cosine function, it's going to start, and there's no offset, there's no phase. It's going to start at 1, and over the course of the period, it's going to come down and then come back to 1. And right in the middle, it's going to be 0, -1. So it's going to cross through the axis here at pi over 4, come down to -1, cross again at 0, and then back up to 1. Does that fulfill what they wanted? Make sure it's at least one complete period. All right, you could continue on if you wanted. So that's my graph. Where do the horizontal intercepts, if they exist, where are they located? The horizontal intercepts. So that means the places where it hits the x-axis where it's 0, and we already talked about it, that's going to be pi over 4 and 3 pi over 4 and continuing on. I guess since we know the period is pi, we could say pi over 4 plus pi n and 3 pi over 4 plus pi n. Probably can coalesce those. It's probably pi over 4 plus pi over 2n, and that'll hit all of them, where n is an integer. By the way, I'm not expecting such a precise and complete answer, but you know, we're trying to get a feel for this. Okay, where are the vertical where is the vertical intercept located? Again, intercepts is where you cross the axis, right? So clearly that's going to be at the point 0, 1. And describe the transformation of the function as related to the graph f of theta equals sine theta, or f of theta equals cosine theta as appropriate. Okay, by appropriate they mean they're talking about here f of theta cosine theta. Everybody can see that. Right? So how does it differ from f of theta equals cosine theta? Well, really the only difference is the period, right? Cosine, without this 2 in there, without this 2, would just be stretched out further. And let's see if I can do this competently. And so forth. So we're just stretching, we're just kind of compressing it by increasing the value of this coefficient. Okay, that kind of beats that to death. Are there any questions about that? Okay. For those of you who like to take photographs, I'll leave this up here for later. Okay, other questions? Other questions on the homework? All right.
Question 38.
38. Okay. Okay, let's zoom on this for a second. Okay, so they're giving you a function, temperature function, models the average temperature in degrees Fahrenheit in Huntsville, Alabama during month M of the year. I'm presuming, they don't actually say whether M0 is January or M1 is January, but it doesn't really matter. Using the function Tm, given in an exercise 37, graph H and T together using a calculator. Describe the similarities and differences. Well, let's take a look. 37. Oh. Ooh, did I sneak something in there? Wait a minute. Well, they say, 37 says use the function in 36. Okay, so that's really, there it is, 36. So let's type this into the calculator here. Calculator on first. Okay, minus 22.75 cosine of, be careful, I'm going to put this in parentheses, pi divided by 6 times, and in this case, x minus 1.
Professor? Professor, but I just asked for 38, not 36. Question.
Yeah, but it says it wants both of them. It says it wants you to,
Oh, can you zoom out?
using the function Tm given in exercise 37. But in exercise 37, it says using the function given in 36. So that's where I'm getting the function in 36 from. So that's the function t. This is the function t, right? So plus 52.55. Okay, so that's the first one. It doesn't look too good yet because we didn't really adjust the. We didn't adjust what we're going from. So probably a good minimum would be, let's say, minus one, and a maximum is probably, say, 14. That'll give us a little more than a year to look at. Now, this is temperature, and so we want the minimum, let's say, Huntsville, Alabama probably doesn't get that cold, but let's say minus 10 degrees. And the maximum, we're going to say 105. And let's see if this starts to look. Well, that doesn't look very good. So that would imply it hardly changes at all. Did anyone get something that looks really different?
We can't see the calculator.
We don't see the calculator.
I'm sorry?
We can't see the calculator.
Oh, I'm sorry. Thank you. So this is the graph I'm getting.
Can you show us the equation?
Yeah.
Is that it? Yeah.
Again, this is the equation from 136. I imagine this is Celsius too. I imagine this isn't Fahrenheit. So my numbers are probably a little too extreme, but I would have thought it would have changed more.
Can you see what you got for graph or window?
This?
Just, well, can you show what the, you got set up, the numbers?
Oh, yeah.
Thank you.
Okay. This didn't work too well, did it? This should be about a year here, a little more than a year. I don't think we might need. Interesting. All right, I'm gonna try just to see if I can find out where my mistake is. I'm gonna switch this over here to the computer and see if I can do this a little better. So minus 22.75 cosine of, I'm just gonna jot in here 3.14159 divided by 6. X minus 1. And then I'm going to add 52.5. And I think I have to zoom out a bit to see this. Okay. Well, that looks little better, except, so it looks like the part we're interested is from, like, say, zero, this is like 2 years here, from 0 to 25, right? 24, 25 months. So, I guess I'm not sure when my calculator is not, oh! Somebody tell me what I'm doing.
Degree radius. Degree.
Yeah, of course. I warn you guys about it, and it fools me every time.
It didn't grab at all.
I'm sorry?
I tried that function on the calculator, it doesn't work. It doesn't grab.
Make the y maximum 105 so you can like adjust to the size.
This is what I get. It's the same function. I was in the wrong mode, right? Put it in the wrong mode, it's not gonna work. Okay, now I'm on track, right? So now, that was the t function, and we want to also put in the h function. So the h function is minus, everyone see this? 18.2 cosine, parentheses, pi divided by 6. X minus 1, oops, key, close parentheses, plus 60.46. Okay, so where are these two models? The first one is Indianapolis. Something seems wrong here, too. What did I do wrong? Negative 22? These should look pretty close, shouldn't they? But they don't. All right. I'm going to try what I did just a second ago because it worked pretty well. I'm going to take a look at the computer, add another function, equation. And now this one is minus 18.2 cosine 3.1415, approximating here, right, divided by 6. X minus 1, and then plus 60.46. Oh, okay, so switching between those, they do interlock, and so I'm doing something wrong in the calculator, even though I can't see it right off the bat. Oh, look at that. There's an extra parentheses in here. So everyone, I'm just going to point it out. So I have 2 parentheses here, but somehow I got a third one in here. So let's see if I can repair my error. Delete. Does that help? Let's see. Okay, so that looks about like what we were going for. I guess it's, there's some kind of lesson, when you beat your head against technology to try and get it to help you. But you can lose track of what this was about. All right, so what they're asking is describe the similarities and differences. All right, someone want to point out a similarity? Obvious one. Let me zoom out a little here just to make it little more obvious. Well, I guess that's not as obvious as I thought it would be. Well, what's really the same about them? Yes?
Well, the maxes are fairly similar.
I'm sorry, what?
The maxes of the periods. They like,
Yes.
yeah, get really.
Yeah, they're close, yeah. But there's something that's really right on.
The period.
The period, yes, yeah.
And angular frequency is also the same, right?
Yeah, the frequency is
Yeah.
also, period and frequency are gonna, if one is the same, the other will be the same.
And then
Okay,
they
let's-
are both horizontally shifted by p/6 radians, like the same shift.
Oops. No, the wrong way here. Yes, yes, they're both phase shifted the same amount, although, we have to wait for it to be finished. In. That's what I wanted. And of course, now it's dead. One more here. This thing has a nice little processor, but it's just beating its heart out to keep up with us here. Okay, this is the view I wanted. Okay, so the period's about the same. The max is very close. You can see here, it's one of them's a little higher, but that's a difference, right? The amplitude's a little different, and the center line is a little higher, which is to say, over the course of the year, it's a little warmer. I forget which is which. You can probably guess it's the one that's further south, right? Alabama, Huntsville, Alabama would be further south than Indianapolis. So, and we'd expect the period to be the same, right? I mean, weather changes with the frequency of the Earth going around the sun, right? Every 12 months. So that shouldn't be a surprise. Okay, it's a lot of words and not that much math. Are there any other questions about this? Any other problems in the homework? Okay. I guess I can digress here for just a second. It's a feature of Foothill Community College that when they teach math classes, for whatever reason they decided this is a good idea. They want this closer to math engineering than math theoretical math. Math theoretical math, we can talk about temperatures, just talk about sines and cosines and whatnot. It's not my preference, but you know, I'm just a teacher here. I follow the rules. So that's why you're going to see a lot of applications. I guess some people feel that, and maybe correctly, that it's more accessible. I'm always open to, criticism or feedback on that. Okay, I want to get back to a subject we talked a little bit about. We talked about the idea if you have, say, a sine function plus some value, say pi over 4. What do we call this value here? Remember? Phase shift. It's a phase shift. So we're going to talk a little bit about phase shifts today. One way to describe a phase shift is in terms of the period. So if, for example, I have a sine wave and I were to do a phase shift of a half, right? That would mean I would move it over 1/2 of a period. I'm not drawing that very well, am I? I'm gonna do it the more cleaner way. All right. So if I were to say sine of x, that's my first function, and I'm now going to move it over. I'm going to phase shift it half a period. So what's the period of sine of x? 2 pi. So if I just phase shift it 9 approximately, okay, it's just going to shift this function here over to here. Right? There's the before and here's the after. It might be a little clearer to show like a smaller shape phase shift. Let's just take a look at quarter. Okay, this is half a pi, which is a quarter of the phase, right? So here's the original, and then, well, actually, since I'm adding, I'm actually moving it over the other way. I want to actually subtract here. Okay. All right, there we go. So I move my starting point over from here to here. That's my phase shift of pi over 4, or 1/4. So, as I was saying, one way to describe this, trying to use some blank paper here, and it's not going to work. My own paper. One way is to refer to a period as 1. That is, if I'm going to phase shift, I'm going to have a phase shift of 1, what am I going to end up with?
Could you
Is
repeat
it
that?
gonna be 1 unit over?
So I take a sine curve and I shift it over 1 complete period. What do I end up with? End up with the same curve, right? So here's the axis and here's the axis.
We can see if you were trying to show it. We can see it.
Oh! Thank you. Just need a big toggle switch here. Now there's a period, a phase shift of 1 is just moving it over 1 complete period. So if I do a phase shift of 1, I'm getting what? I'm getting my function back, right?
Wait, question?
Yes?
So you're moving 1 period, or is it moving
1
by
period.
1 unit? Okay, 1 period.
A phase shift of 1. Now let's be careful. If this function is sine of x, the period is 2 pi radians. So we're really talking about a relative scale, relative to the function. In other words, whether this is sine of x or sine of 2x or sine of half of x, a phase shift of 1 does the same thing. It just moves it 1 period. So that amount
Whatever.
differs. It's the period, right? That's one way to refer to a phase shift. Another way is to say the phase shift of 1 is equivalent to 360 degrees. All right. That is, a phase shift of 360 degrees just moves the function over to itself again. That's a different way of referring to it. Okay, I'm going to give you a nice real-world example here. We're going to look at the power that comes out of the wall. This is what US plugs look like. Either two prongs or you can have a ground wire. And the function here oscillates between plus 110 volts and minus 110 volts. And the frequency is 60 cycles per second, right? So the period is 1/60th of a second. So that's standard US power coming out of the wall. There's some variations. Canada, some of it's 110, 60 cycles, some of it's 50 cycles. It's different.
Professor?
Yes.
I think he's gonna say the same thing. It's 120, I think.
I'm sorry?
According to the problem, it's 120, not 110.
120. Yeah, I don't know why I said that. I don't know why I said that. So that's usually 120. It actually, there's a tolerance. I think maybe that's what I was thinking of. You can have you can have it vary a certain amount. Does anyone know what happens when it goes below kind of some critical value? Anyone know the term we give for that? Heard of a brownout?
No.
Heard of a brownout? No?
Yeah.
Yeah. That's not the same. A blackout is nothing, right? But a brownout is you get down below, say, 190
So what happens?
90 volts. Well,
Your device
some-
blows up.
some things work and some things don't. The lights still work. They don't look, fluorescence may not work. Incandescence will work.
Heaters still work. Heaters still work.
Heaters still work, that's right.
There's countries that use 240, so it's not.
You're getting ahead of me here. Okay. So in Europe, they use 220 volts, which I just have a diagram here showing 220 on top of 110. It's usually still 60 hertz, and the plugs look a little different. Any Europeans here? Can you confirm this? This is what the plugs look like?
Yeah.
That's what normal plugs look like.
Although, I've seen this kind, two like little round plugs,
Yeah.
and does it matter? Are they all the same? It's just
No,
the one on the left.
Okay, it's different from like most European, like, I know when I went to like London Airport, there's a completely different one than like Germany or like.
Isn't that one like Australian?
I haven't, that
I know that in Australia they have completely another one.
Yeah.
Yeah,
Okay.
it's different.
But again, these are, just to be clear, it's all alternating current, right? The advantage to 220 volts is there's more power coming through. The disadvantage is it's easier to electrocute yourself, right? You can electrocute yourself with 120, but it's a little easier with 220. Okay, now, finally, because we want to get to phase shifts here, for industrial applications, at least in the US, we can get this very special kind of power source. It's called three-phase. So what you have here, you see this connector has 4 different connectors. One of them is a ground wire, and then 3 of them are have a voltage that goes, just like our 110 goes up and down, right? But if you look at this diagram here, you see, here's like 110, right? And here's 110. And then over here, here's 110. You get 3, it's like 3 plugs, but they're intentionally out of phase 120 degrees, 120 degrees, or 1/3. And the reason for that is it provides smoother power over the course of this. When the voltage is 0, you can't get any power out of it for that brief instant. So during the course of the AC going up and down, you can extract power from it, but it's not very smooth. So again, this is a really good application the idea of phase. Okay, are there any questions about that? It's unlikely this will be on the next test or exam, but it's interesting stuff. So. Okay. Good? All right. What we're going to do now is we're going to learn, so we learned about periodic functions. We learned how to graph them. Now what we're going to look at is how to look at some data which we believe to be a sine or cosine function, and how to model it with a particular function. How do we get from the data to the function itself? First thing I'm going to point out is that if you look at the sine and the cosine function, they're really the same function, just phase shifted. So we don't really need to worry which we use. We can use either a sine function or a cosine function for our model. And the only difference will be the phase. It might be more convenient to use one or the other, but we'll get into that in a minute. So again, I want you to take a look back at this generic function where we have some coefficients A, B, C, and D, and we want to figure out how to find what these coefficients are for a particular set of data. Recall, of course, the amplitude is what?
We can't see the graph.
Oh, you can't see this?
The graph.
There's no graph.
Oh, there's
I'm asking for the definition,
Oh.
right? The amplitude is what? It's the maximum
Minus the minimum divided by 2.
minus the minimum divided by 2. Right? Frequency, or the period, we're going to get, by looking at where does the data repeat. And D is going to tell us where the midline is. Right? All right. So let's take a look at an actual example. All right. So I have some data here. The x-axis, it doesn't really matter where we start in particular, but as long as we know between each reading, it's just 1. Okay. So let's look at this data. What do we see the maximum as?
6.
Okay. There's our maximum, and our minimum.
2.
Oh, 4.
No, that's the x coordinate. We're looking for the minimum of the y coordinate. Okay, so we see 2 over here. All right. So our amplitude is our max minus our min divided by 2. 6 minus 2 over 2 is just going to be 2. Okay, good. All right, now we want to find our midline. That's just, again, 6. Now it's 6 plus 2 over 2, or 4. All right, now let's see if we can figure out what our period is. Okay, so we want to find 2 places along here. We want to find where it matches. So it looks like from 5.2 to 5.2 is what? 1, 2, 3, 4, 5, 6, 7. All right. How about, wait a minute, hold on. That's a 5, 2, but that's a 5, 2, right? This is 4, 5, 2, 4, 5, 2. All right, so we want to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it looks like the period is 10. All right, well, if the period is 10,
Isn't the period 5? From 4 to
oh,
4?
well, no, wait. There's a 4 in front of this 5, 2. There's a 4 in front of this 5, 2. So they match. There's another 5, 2 here, but there's not a 4 in front of it.
Oh, so is the following y coordinate after
Well, you know, maybe, you know, we're gonna graph these points in just a second, so we'll actually see, but we'll see that it's not a smaller number than 10, right? Okay, but so what does B have to be? The period is 10, right? We've got to back up here a little. Recall that the period is 2 pi over the absolute value of B, right? So the period, so B is going to be what? The period is 2 pi over B, then B is 2 pi over the period, right? So it's going to be 2 pi over 10 or pi over 5. All right, we're going to graph that in a minute, but first let's just plot some of these numbers here to get a feel for this. For minus 2, we're up here at 6. For minus 1, now we're at 5.2. At 0, we're at 4. At 1, we're at 2.8. At 2, we're now down to 2. 3, now we're back at 2 again. And then at 4, we're back up at 2.8. And at 5, we're at 4 again. And at 6, we're at 5.2 again, right? So this starts to look like a sine function, right? Let's put this together, right? We haven't really figured out the phase shift yet, but we can wait on that a little. Okay, so we know our amplitude is 2. So let's do it this way. Let's say our function of x is 2, and let's use the sine function. All right. Our b we know is pi over 5. X minus c, that's going to be our phase. We don't know what that is yet. And our d we know is 4. Right? So, okay, let's think about this for a minute. If we're using the sine function, where, you know, our c value is going to be where it starts, right? And the sine function starts at the midline, right, which is 4. So this point here, which is at 5, right, that would be one place to start, right? So that would make C 5. All right, let's check this out now. So we have, for our model, 2 sine of pi divided by 5 times x minus 5 plus 4. So we're probably going to have to play around with the axis on this. Okay, so we want to run this. Let's run it the same as our graph here. So from minus 2 to, how far does this go? To 11. And our minimum, we can just make that 0. And our maximum, let's put it a little bit above where we are. approximately, so it's 6, so let's think 8. And let's see what the graph looks like. Oh, we forgot something, didn't we? That doesn't make sense. Oh, because I put the parentheses in the wrong place. There we go. Okay. Does that look like our graph? Everyone see that? So that's what we're doing here. We're taking something which we believe is a sine curve, and we're taking data points, and we're using those to match it to our curve. Right? How are we doing here? We're doing okay. Let's try one more. Okay. Again, we have some data points here. Note that the x scale is a little different now. Each of these data points is, differs by 5. So the max on this looks like what?
1.5.
1.5. Zoom in a little bit better. Okay, the minimum looks like it's
0.5.
0.5. So our amplitude is now going to be 1/2 or 0.5. The midline is now at 1. Okay, so now we want to start looking for where this data repeats. Now, I have to tell you, in a real scientific experiment, the data might not look quite so nice. It might be periodic, but you're taking a measurement, so there might be some tolerance here. But in any event, it looks like the period goes, we have 1.3 here, and 1.3 here. So what is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But it's not 10, it's 10 times 5 or 50. Okay.
What did oh yeah,
Wait, why is it 50?
because it's going 50 from 0 to 50, that's where
Oh, God.
Okay. So now, what did we decide our b is? Our b has to be 2 pi over 50. And now the only issue is what is our phase offset? What is our c value here? Okay, so just to give you a little different way to look at it, the c value is the point where you're on the midline and the sine curve is going up. That's if we're using a sine curve as our model. All right, so let's take a look at this data. The midline is 1. So it looks like we're at 1 here, and we're moving upwards. So it kind of looks like the c will be equal to 0. All right. Let's plot. See if we can plot this. So at 0, I'm going to have to adjust the scale here. So this is 5 and 15 and so forth. So we start at 0, we're at 1. And then we go to 1.3, 1.5, 1.5, back down to 1.3, back down to 1, 0.7, 0.5, 0.5, back up to 0.7, back up to 0.1. Okay, so our model says this should be what? F of x should equals a, which is 0.5, times the sine of 2 pi over 50, or pi over 25, times x minus, well, since it's C is 0, it's just going to be x, and then plus 1. So let's try looking at that function. Trying to keep these on the same. Okay, so 0.5 sine of pi divided by 25 times x plus 1. Now I know I'm going to have to adjust my window a little. Let's start this at 0, and let's go to 55. And we can have our minimum at 0, but we only need to go up to 2 here, right? Well, once again, it looks like I've done something wrong. Oh, I put an extra one of these guys in here again. And need here. Aha! Did everyone see that?
Go to.
No, it's the unavoidable error syntax, which means what I have to do is go look at my function again and see where I did something wrong. So
There is an extra
pi plus
parenthesis.
25. Oh, yeah. There we go. Okay, trial and error. And here we have our function, just like on our graph here, going between, I don't know if you can see this, but it's going between 1 and 2 here, looks like. Sorry, it's starting at 1 and it goes up to 2. No, it doesn't even go up to, it goes up a little below 2 and then a little above 0. Except it doesn't look right. It's still plus 1.5. Huh. I guess I need to take a look at my scale here. Oh, I don't know. This is just telling me where to make the little marks on my scale. And these we probably want to make every 5. And now I can't even see marks. All right. Any questions about this process?
I'm still not understand why you can figure out C so quickly.
Oh, how can I figure it out so quickly? Well, in this particular case, all right, this data here, I know that this is like, even though I've drawn the axis here, this is C. This is where the sine function is at the midline and starts moving up. So I look at my data here. My midline is 1, so I look at all the 1 points, right? This one is moving up. This one is moving down. That's over here. And then here I'm moving up again. So I also, I could say C is 50. That's what a period is, right? Let's look at the first one again here. Here the midline is 4. So I look at the data. I see here the data 4 is moving up at this point. Where did I decide the C was? Oh, well, I guess I could have said C is 0, right? Because the period is, well, that's not quite right. Oh, minus 5. So I could have used C either minus 5 or C plus 5. Right? At either of these points, we're at the midline and we're moving up. Right? Now, just to be clear about this, let's say I was modeling something with a cosine. The cosine at C is at the maximum and it's moving downward. So if you wanted to model one of these with a cosine, we could try that. This data seems a little easier to deal with. Okay, so let's look at this data. Where does it reach its maximum? It's about, kind of reaches it between 10 and 15, it looks like, and then it moves down. So if we use the cosine, we could pick this point here.
Could you zoom out a little bit?
Oh, sorry, thank you for letting me know. Yeah, at this point here, which is 12.5, and we could say, in this case, f of x equals 0.5 cosine, everything else is the same, over 50 minus 12.5 plus 1. And again, these are, it's the same function, but this function and this function just expressed as a sine or a cosine with a phase difference.
So this is all like visual kind of.
Yeah.
And if it's either cosine or sine, you can shift it,
That's right.
so you can build it and everything.
That's right. Either, one may be more convenient than the other. For example, if you see immediately that at 0, your maximum, you're at your maximum and you're going down, you might want to use a cosine instead of a sine. Just because it, then C, it looks better because C is 0, right? Okay. So I have a worksheet for you. You have a few minutes to work on that. Let's take a look at this. The first 3 questions are pretty elementary. And then there's a problem like the one I did on the board. And they're more running over this way. Who doesn't have one? Who needs one? Just take one and give the rest back. Okay, thank you. That's all. I think we lost a few souls. Got demoralized by that quiz, I guess.
Ну, и же нельзя будет его сколько. Я знаю, сенсорная все. Я полгода назад. Надеюсь, они в маленький уже встроят обычный видеокамеру.
Не, на видеокарту вообще не смотрю, для этого записи стоит. На маке играть в таблете.
Во что ты играешь? Во что играешь?
Ну, сейчас не времени. Стратежки раньше.
Okay, so just to be clear on this first 3, when I say the phase shift, I'm really looking not for the period shift. I'm looking for that number either, using the scale 1, meaning 1 period, or 360 degrees. And these diagrams being a little not all that accurate, I'm not looking for an exact answer, I'm looking for an approximate answer.
Просто в единицах. Мне кажется, все
For this? Oh, okay. So we have a sine function. C is the point where it crosses the midline and it's going up. If you're doing a cosine, it's the point where, this is C, the point where you're at the max and you're going down. Now, this actually assumes something which I haven't stated, but we've been working with, which is the idea that we're using an amplitude greater than 0. Or let me rephrase that. The amplitude is always greater than 0. But if the sign in front of the function is positive, right, or in this case, cosine is positive. So actually what I just said about this, you could model it and have a minus sign in front. But then what would happen? What happens if you have minus sign of something? What does that look like?
It will flip.
It's flipped, right. So in the case of the sine, it would be the point where you're at the midline and you're going down. I hope this isn't, I hope you understand. There are a number of different ways you can write the same exact function, right? Sine and cosine, you can write the same function by phase shifting. And likewise, by changing the sign in front, the sign, plus or minus, because the sine function, it has all these symmetries here, right? Not only every period is symmetric, but you can flip it over and move it half a period, and you get the same function. Let me demonstrate that. So if I say sine of x, or if I say minus sine of x minus pi, which is half a period, I get the same thing. I claim. So why not? I just demonstrate that. Say sine of x and minus sine of x minus pi. I graph these, so let me give us a little better window here. So what you're not going to see here is that's the first graph, but you don't see the second graph because it's just overlaying it. We kind of prove that to you by taking one of them and I could say, so I added I changed the midline, right? I just moved it up. But these two overlay each other perfectly, right? Because like the minus sine of x is just the flip of sine of x. And it looks the same if you move it half a period. All right. Someone want to look at the first one of these and tell me what they think the phase shift is? So, like this is the period here. Looks like it's 3. And how much have we shifted here?
1
unit?
1/3.
Yeah, actually, it's about 1/3,
About.
right? Although if you look at it, you can actually, you can be a scientist and you can say, it's kind of like 0.9, right? Right? So, like 0.9 over 3, or instead of 1/3, it's about 0.3.
Professor, excuse me,
Now, what is that in degrees?
question?
Well, that's just,
Professor?
yeah.
You got a question.
Thank you. How is that a period? Like, could you show the picture again? Yeah, is that a period?
Oh. You know, you're right.
It's not a period.
You're the only student who got that right. Everybody else failed. That's not a whole period. That's half a period. 1.9 over 6, or 0.15. Thank you. Yes? In other words, the whole period is 6 units here, but the phase shift is about 0.9. So 0.9 over 6 is about 1.5. Thank you. And in degrees, that would be 0.15 times 360. It's about a phase shift of 54 degrees. All right, let's look at the next one.
Hold on. Question?
Yes?
Okay, so you did 0.9 over 6.
I'm sorry.
Okay, you did 0.9 over 6 and you got 0.15. And then where did the 360 come from?
Oh, okay, so there's two ways to describe a phase shift. You can describe a period as 1, or you can describe it as 360 degrees.
Okay.
Right?
You can just.
So you'll run into both of these in different contexts. Here's a context we just talked about where you will, let's see, where did that go?
Where did it go? You can also describe it as 2 pi.
Remember, the period is 2 pi, right? So you could talk about the actual amount on the x-axis. But what I'm referring to here is relative. Let me rephrase this. All right. So here's an example of 100. Typically with 3-phase, you talk about it being 120 degrees out of phase, 120 and 240 every third. Now, if you said, okay, this is 2 pi over 3, right? Well, 2 pi over 3 what? Right? These are cycling 60 times a second. So 2 pi over 3 times a 60th of a second. Right? But if we change frequency, let's say we go to 50 hertz,
You have to
then this
adjust
number changes.
It's like a ratio.
Right, it's a rate, that's a good way to put it. It's a ratio, and it's relative to the period of the function. This, again, we're talking about phase shift. We're not talking about period, we're talking about phase shift. So a phase shift of 1 is 1 period, whatever that is.
Yeah,
Right? It could be 2 pi, or 5 pi, or 6 pi.
yeah, it comes into that.
Phase shift of 1 is always 1 period.
It comes into like the multiplier on the angle.
I think if I understand you, yes. All right. So again, back to our problem. It's 0.15 or 54 degrees. All right, let's take a look at the second one. I think this one was a little easier. So let's figure out our period correctly this time. So this is 1, 2, 3, 4, 5, 6 point something. Probably is 2 pi, right? So how much is our phase shifted here? Right?
Is that reflection?
Over.
Is it this reflection?
Reflection.
No.
Oh, well, no, not quite. I mean, they're a little, a reflection, I think what you mean is like half a period. Like, you know, one is up and the other is down. But if you look, these are a little askew, right? It's not quite a period. Let's figure it out. Let's calculate it. So the starting point here is 0. This is 1, 2 point something, right? Let's say 2.2. So it's going to be, let's say 2.2 over, I'm just guessing that, you know, the way I graphed it is really 2 pi. So let's find out what that is. So 2.2 divided by 2 pi, when in doubt, put parentheses. So it's a phase shift of about 0.35 or 126 degrees. All right. Okay. We'll kind of run out of time. On the back, you'll see 2 examples. Maybe it'd be a good idea to try these for homework. And there's also an assignment along with this. Yeah. Put up the assignment here. It's going to be on the website as usual. Okay. So, the assignment, let's finish up the Wednesday. C is the phase, or is it's this number.
This one probably is the whole equation. That's why I got 2.
Because the whole base is 6, so we're just going to say like, that's the whole thing, so it's like 360 degrees or 2
So it's just easier to say 2 pi. So 2 pi is probably, here, hold on. Let's find the
Did you want more time on your? Yeah.